Hello guys, so in this video I'm going to show you how to solve some problems regarding specific heat, or how to understand the concept of specific heat in chemistry. Okay, so we have a problem, we have a table that has a different list of metals. In here we have aluminum, we have copper, we have gold, iron, silver, and I'm also going to add water just as a reference to explain this principle of specific heat. Okay, so what is specific heat? So we can understand what specific heat is by looking at the units that specific heat has, right? Which is joules per grams per degree Celsius. What this means is that specific heat is going to be the amount of joules, or how much energy you need to input into a sample so that 1 gram of that sample increases 1 degree Celsius in temperature. So this is basically a unit of measuring how much heat a sample can absorb before it increases its temperature. Okay, and it has to do with mass because there's specific heat and there's a specific heat capacity. So specific heat capacity, it has nothing to do with mass over here, right? But we're talking about just normal specific heat right now. So how much energy a sample has to absorb in order to increase its temperature. Okay, so the problem says if the same amount of heat is added to 50 grams, or 50.0 grams of each of these metals, so all of them have the same amount of mass, right? And all of them have the same starting temperature, or T1, right? Which of those samples is going to reach the highest temperature? Okay, so we're adding the same amount of heat to the same amount of mass to the same starting temperature, right? So which is going to reach the highest temperature? Now you can do all of this mathematically, but by using the formula Q equals mass times specific heat times the change in temperature, or temperature 2 minus temperature 1, right? Final temperature minus initial temperature. Or you can just put a little bit of thought on this, okay? And that's the reason why I put water into this example over here, okay? So the specific heat of water is going to be 4.184 joules per grams per degree Celsius. Okay, and this means that it takes that many joules, or that amount of joules, in order to increase the temperature of 1 gram of water by 1 degree Celsius. Okay, so as you can see, the specific heat of water is relatively larger. It's in the next order of magnitude larger than the specific heat of the metals. So what does this number tells us? Picture yourself, or think about this. Right, you're going to put 2 pans in a stove, exact same pans, exact same size, right? And then on one of them, you're going to fill it up with water. You're just going to put some water in there. Then you're going to turn on the stove. So you're going to be heating this, let me just make a quick sketch here, right? You have 2 pans, and you're going to heat those 2 pans, but one of them has some water in there, right? And let's say you're going to heat them up for about 1 minute. Which of these 2 pans is going to be, or is going to burn your hand, right? If you put your hand inside the first pan, chances are you're going to get burned, right? It's just a pan, and it absorbs a lot of heat, and it raises up its temperature. Or in other words, it absorbs, let's say we're heating them up for the same minute, so they are being exposed to the same amount of heat, right? The same amount of time under the flame. But one of them is going to be quite warmer than the other one, right? So this is going to be the aluminum pan by itself, and it's going to be really, really hot. That means it absorbs most of the heat, right? So it absorbs a little bit of heat, and then it increases its temperature. Then it absorbs a little bit more of heat, and it increases its temperature again. That's why it reached a really, really high temperature, and that's why it's burning you. But if you put your hand into this pan, that's basically water, right? The pan, any heat that's absorbed by the pan is transferred into the water. This water is just going to be slightly warm, right? You're not going to get burned. That means that you need to have at least 4.184 joules in order to increase the temperature of this water by 1 degree Celsius, right? So the larger the specific heat, it means that you require more heat to warm it up. Okay, more heat per gram in order to increase a degree Celsius. Okay, so by using this relationship, which of those metals is going to be the one that reaches the highest temperature? that is the completely opposite of the largest specific heat. As we can see, we will need to leave this water pan in there for, I don't know, I'm just gonna make a sketch, maybe 5 minutes in order to start getting it warm, right? But if you leave this pan by itself 5 minutes, that pan is going to be piping red, right? The temperature is going to be really, really high because the specific heat of aluminum, as you can see over here, is way lower than water. So it means that it requires less heat in order to warm up, right? So since you're putting the same amount of heat to all of the samples, well, the aluminum is going to have a really, really high temperature. Copper, in relation with aluminum, it has a lower specific heat. So the temperature on that, if that pan was made of copper, it will be even, even higher because it has a lower specific heat. What about gold? You don't really want to put your hand into that gold pan. Okay, that specific heat is really low. It means that it requires just this tiny amount of energy to increase its temperature. Okay, so this temperature on the gold, I'm just gonna put some extra arrows in there because it means it's really, really high. Okay, now for iron, I'm just gonna switch to green over here, right? So that specific heat is more or less the specific heat of copper, a little bit higher. So that means that the temperature on this iron is going to be a little bit lower than the copper, but still somewhere around the copper because they have really similar specific heat, right? And the last one, which is silver. Silver has a 0.235 the specific heat joules per grams per degree Celsius. So this number, I want to say, is more or less like copper, a little bit less than copper, So the temperature is going to be, I want to say, just 5 of those, right? A little bit higher than copper, a little bit lower than gold, which is the highest one, right? And of course, the one with water, what is going to be the temperature in there? It's going to barely increase. Why? Because you need this much energy in order to increase its temperature by 1 degree Celsius. Okay? Of course, you can do the mathematical calculations. I'm going to do that right now. Okay, I'm just going to do it for water and for gold, just to show you what the difference in the final temperature is going to be. Okay? So the formula, again, Q equals mass times specific heat times the change in temperature. Okay, so let's do for gold. So the heat, the problem says that they are all going to be exposed to the same amount of heat. Okay, what this means is we can just make up some number, and I'm just going to say the heat is going to be 10 joules. And that's going to be the same for water, right? Let me do water here. Right, 10 joules. We're putting the same amount of heat into those two. Well, there were supposed to be 2 metals, right? But now I'm choosing water just to prove a point. Okay, you can choose any other metal, and you'll see that gold is going to be the one that increases the most temperature. Okay, so what is going to be the mass of those samples? The problem says that everything is going to be 50 grams. So let's go ahead and substitute 50 grams instead of the temperature, right? 50 grams over here, or 50.0. Let's go ahead and keep the correct number of significant figures, right? 50 grams. The specific heat is what's going to change. So what is going to be the specific heat of gold? We go back to our table. The specific heat of gold is going to be 0.128. So let me just erase that. 0.128 joules per gram degree Celsius, right? That's the specific heat. And the specific heat of water is going to be 4.184, same units. And I'm doing the 2 problems simultaneously. Then the last thing that I'm going to place in here is going to be the change in temperature, right? So let's go ahead and place the change in temperature. What is going to be my initial temperature, or my final temperature in that case? Well, it doesn't really matter, right? Well, they all start at the same temperature, right? They all start at the same temperature, and we're trying to find what the final temperature is, right? So T2 minus T1. So T2, this is what we're looking for, right? And temperature 1, as long as they all start at the same temperature, what's going to be the starting temperature? It doesn't really matter, right? I'm just going to come up with a number in here. I'm just going to put 10 degrees Celsius. As long as they both have the same, starting temperature, right? That's what the problem says. Same amount of heat same amount of mass at the same starting temperature, which is going to reach a higher temperature? Okay, that's the question. Okay, let's go ahead and continue doing this problem over here. So let me just simplify. Let me just solve for the variable that we're looking for, which is T2. Okay, so let me just move this guy over here a little bit. So I have space to work on the gold. Let's go ahead and solve for T2. So I'm gonna get rid of everything that's multiplying this part of my formula. So everything that's multiplying over here is going to go dividing to the other side. So 10 joules divided by 50.0 grams, and that's also being divided by 0.128, the specific heat. Right? Everything's multiplying, and all I have left in the right side is going to be T2 minus 10 degrees Celsius. Okay, and the last thing that I'm going to do is send this negative, or this subtracting 10 degrees Celsius, to the other side with the opposite operation. So the opposite operation of minus is going to be a plus. Okay, so this is going to end up looking like 10 joules divided by 50.0 grams, and 10 joules is also divided by 0.128 joules. And to all of this, I am going to add my 10 degrees Celsius, and that is going to be the result, the final temperature of gold. Okay, and can you see that the formula is going to look the same for water? The only difference is going to be the specific heat that we're placing in here. Right, my specific heat is 4.184 joules per grams degrees Celsius plus 10. That's going to be my temperature, my final temperature of water. And over here on the top, that's going to be the final temperature of gold. Right, just put in the symbols. So let's go ahead and do the math. So the first thing that I'm going to do, let me just have some more space for the water now. Right, the first thing that we're going to do for the gold is going to be the cancellation of units. Let's see what's going to be the unit that's going to be left, okay? So I have joules on the top and I have joules on the bottom, okay? And then I have grams. This is going to be a grams that's on the top. If you look at this part only, that's a grams on the top, and this is a grams on the bottom. So those are going to cancel out, okay? And the only thing that I'm going to have left is going to be the degrees Celsius in here, okay? So those degrees Celsius, that's going to be the unit that's going to carry over to the result, right? Degrees Celsius plus degrees Celsius, the result is going to be in degrees Celsius. So we're good. Let's go ahead and do the operations. So I'm going to multiply 50 times 0.128 in my calculator really quick. Okay, so that's 10 joules. Well, I'm not going to include the units anymore since we already know what the unit is going to be. 10 and 50 times 0.128, that's going to be 6.4 plus 10. And then 10 divided by 6.4, it's going to be 1.5625. And then plus 10, the result is going to be 11.5625. So that's going to be the final temperature of my gold. If I put 10 joules, that's going to be the final temperature of the gold. Okay, let's go ahead and do the same calculation for the water. I don't know why my water turned this new color. Just go back real quick. I don't know why my water turned dark in here. Okay, same operations that we're gonna do right now. So 50 times 4.184. So it's going to be 100 joule. 10 joules divided by 209.2. I'm not going to include the joules anymore. And plus 10 degrees Celsius. That's going to be my final temperature. So 10 divided by 209.2 plus 10. The result, or the final temperature in here, is going to be 10.04 degrees Celsius. So can you see the impact of a lower and a higher specific heat? So with the same amount of heat, the same mass, the gold sample increased about, 1.56 degrees, and the water sample, it barely increased its temperature, right? It barely increased from 10, which is the starting temperature. That's my starting temperature. It increased 0.04, not even a tenth. I mean, a little bit, not even a tenth of a degree, right? So it increased very, very little because the specific heat is higher. So now I did the calculation with the highest, going back to the table, the highest specific heat that I'm showing here, and the lowest specific heat. So if you do the calculations for the numbers in between, you're going to get some temperatures in between, 1004 to 11.56. But it all has to do with the specific heat, right? So for example, if I give you some other metal that, I don't know, I'm just gonna make that up, right? A new metal. And the specific heat for this metal is 10.01 joules per grams degree Celsius. So this metal, the temperature, if you plug that into the same formula, the temperature is going to be even higher, right? It's going to be even, it's going to be even lower. It's the opposite, right? The higher the specific heat, the more heat it absorbs before it increases its temperature, okay? If I were to put another metal in there that the specific heat is going to be, 0.09, even lower than gold, then this thing is going to heat up even more, right? It's going to heat up even more with the same amount of heat input into this experiment, right? So this is one of the problems, and I think this is one of the most complicated problems because you do have to think about it. You have to put your mind on it and do something that I call a thought experiment, right? Like this little drawings of the pan. So picture yourself, right? Which is going to be warmer, which is going to be colder. And sometimes that helps you a lot into solving some of these problems without even getting into the math, okay? So please let me know if you have any questions. And I'm going to put my channel over here, Math from a Mortal, right? This is where I'm going to upload this video, and I have some other videos in there for you to see. So let me know if you have any other questions.